So I'll just go over all the problems in the test. Although I think some of them more people got than others. So we can do some of them together, and then for the ones that people found a little bit harder, I'll explain them. Cool. So again, like every other one on the test was kind of probability related. So I'll just go through all of mine, and then we'll go through the problems from Mathew. So this was the first question I put on the test. It said a box of cookies has 3 types of cookies. So we have sugar cookies, chocolate chip cookies, and oatmeal raisin cookies. And then we're given the facts that there's 3 times as many sugar cookies as chocolate chip cookies, and the ratio of sugar cookies to oatmeal raisin cookies is 2 to 3. Alice randomly takes a cookie from the box to eat. What's the probability that it's an oatmeal raisin cookie? So actually a lot of folks got this problem correct. So anyone want to share how they did it?
Well, when I was solving the problem, I tried to use the information already given, and I just assigned variables to each of the types of cookies. So I wrote an equation down sort of like 2 sugar cookies plus 3 oatmeal raisin cookies plus C equals 1 as their probability, as like the total, sorry, X, which is the total number of cookies. And then after that, I just tried to use the information like the fact that there's 3 times as many sugar cookies as chocolate chip cookies. 3 doesn't divide into 2 evenly, so I multiplied by 3 to get 6. And of course, I had to multiply the number of oatmeal raisin cookies by 3 as well to get 9. And so I ended up with 2 regular cookies, 9 oatmeal raisin, and 6 sugar. And so when they asked for the oatmeal raisin, I summed. So 9 plus 6, 15 plus 2, 17. And then I just took the number of oatmeal raisin cookies as 9 over 17.
Cool. I think that's a good summary. Let me try to write it out so everyone can see. So if I'm understanding correctly, you had variables for each of the numbers of cookies, and then based on what we're given in the problem, you wrote some relations around them. So the first one is there are 3 times as many sugar cookies as chocolate chip cookies. So that would give you, what was the equation?
Was I wrote it down as 2s plus 3o plus c, which is the different cookies, equals x, which is the number of cookies. And I had it down that 2s is equal to 6c.
Okay, yeah, I think you could just write s equals 3c here because it's telling you, I mean, it's the same thing. You just have multiplied by 2 on each side. But when it says 3 times as many sugar cookies as chocolate chip cookies, then we know that if we take the number of chocolate chip cookies and times 3, that will give us the number of sugar cookies. The second part that we're given is the ratio of sugar cookies to oatmeal raisin cookies is 2 to 3. So that's telling us S over O equals 2 over 3. And then the quantity we want to find is probability. Alice picks an oatmeal raisin cookie.
Miss Wendy, are you writing? Because we can't see it on the screen. Well, I can't see it.
Sorry, it said it was paused.
Yeah, I can see it now.
Okay. You see it? Sorry, so I just wrote down these 2 equations, S equals 3C and S over O equals 2/3 to capture these 2 parts of the problem that I highlighted. And then the probability that Alice takes an oatmeal raisin cookie is going to be O, which is the number of oatmeal raisin cookies in the box, over the total number of cookies in the box. So that's going to be S plus C plus O. So let's see if we can use these equations to write this fraction into something that we can simplify. So from the second one, S over O equals 2 over 3, we basically get S equals 2/3 O. And then if we want to plug that into this equation, then we get 2/3 O equals 3C, or C equals 2/9 O. So now we can plug this into here and this into here. Then we'll get O over 2/3 O plus 2/9 O plus O. And so now we can actually cancel out this variable because we don't actually need to know how many cookies there were. We just need to know the relative ratios of the types of cookies in the boxes. So this will give us 1 over 2/3 plus 2/9 plus 1, which is 1 over 6 plus 2 plus 9 over 9, which is going to be 9 over 17. Cool. 7. Anyone have any questions about this one? Cool. So one note on this is sort of the like algebraic approach to it. I'm guessing another way like people could have done this is since if you realize early on that the total number of cookies doesn't really matter, and what you're really after is this ratio, then you can kind of say, okay, if there's, you know, what's the sort of like minimum number of cookies we can have to satisfy all of this? So you could say, okay, if there's like 3 times as many sugar cookies as chocolate chip cookies, you could say, okay, so if there's 1 chocolate chip cookie, then there's 3 sugar cookies. And then you know the ratio of sugar cookies to oatmeal raisin cookies is 2/3. So you could say, okay, maybe there's, you know, 6 sugar cookies and 9 oatmeal raisin cookies. And then that would mean that there's 2 chocolate chip cookies. So then you would get, I'll write this down. So if S over O equals 2/3, you could say perhaps there's 6 sugar cookies and 9 oatmeal raisin cookies. And then since S equals 3C, then we could say there's 2 chocolate chip cookies, which is not actually necessarily the number of cookies, but that's the right ratio. And then you would get 9 over 6 plus 9 plus 2, which is going to give you the same answer. All right, I'll move on to question 2, unless there are any other thoughts or questions about this one. All right. So this question says there's 10 marbles in a jar, some that are green, the rest of which are blue. When Brian randomly takes 2 marbles out of the jar at the same time, the probability that both marbles are blue is 1 over 15. How many marbles in the jar are green? So any thoughts on how to do this one?
I tried to think sort of backwards with this one. I didn't really get it, but I was thinking along the lines of, well, there would be 3 cases for how many, for the different color combinations of 2 he can take out. you can take out green, green, blue, blue, or green, blue. So I said there was a 1/3 chance. So I tried to remove the 1/3, divide by 1/3 for this just to start off.
Where's the 1/3 come from?
Because there's 3 different cases for the different color combinations of 2 that he can remove from the 10 marbles. So I tried to divide by 1/3 the probability of them both being blue, just to start off.
I see. So in this case, because the number of green marbles might not be equal to the number of blue marbles, we can't assume that these probabilities are all the same. So the probability that you pick 2 blue marbles is going to be different than the probability that you pick 2 green marbles, potentially. And then also the probability that you pick a green and a blue marble, since there's kind of 2 ways you could do that. You could pick a green and a blue, or a blue and a green. It's going to be also different than the probability that you pick 2 blue marbles and the probability that you pick 2 green marbles. So one thing you could do here, similar to the previous problem, is we can use some variables to help create like equations to represent the relations we do know, and then try to solve for those variables to deduce what we're looking for. So in this case, we know something about the number of blue marbles in the jar. So maybe you could say let B equal the number of blue marbles. So if there are B out of 10 blue marbles in the jar, and Brian randomly takes 1 marble out of the jar, what's the probability that it's blue?
The number of blue marbles over 10.
Yeah, so if Brian takes 1 blue marble, that's going to be B over 10. So what we're given is if Brian randomly takes 2 marbles at the same time, the probability that both marbles are blue is 1/15. So what's the probability that Brian, sorry, I spelled his name wrong. What's the probability that Brian takes 2 marbles in terms of B?
Would that be B choose 2 over 10 choose 2?
Yeah, so and we could simplify this to B times B minus 1 over 10 times 9. And then we know that this probability is 1/15, because that's what was given to us in the problem. So we can write this equals 1/15. So now we have this equation that we can, or maybe I won't say it because I do that with the answer. But we now have this equation that we can solve. So let's bring this over here. We could basically, I'll just rewrite it. B times B minus 1 over 10 times 9 equals 1 over 15. So we can cancel some stuff out here. So 15 goes into 10 over 9, or 10 times 9, 6 times. 6 times 15 is 90. So then this gives us B times B minus 1 equals 6. So there's a couple ways you could solve this. You could kind of expand out the quadratic and you'll get B squared minus B minus 6 equals 0. And then, sorry, the B's look a lot like 6s. But these are the B's. Or we could also kind of notice that 6 is 3 times 2, and B times B minus 1 is you're looking for a number times 1 less than that number to equal 6. So you'll kind of get that B equals 3 from that. You also get, if you fully solve the quadratic, you'll also get the solution b equals -2. But we can actually disregard the solution because we know that b is a number of blue marbles, so it can't be a negative number. So once we know that b is 3, we know that number of green marbles in the jar equals 10 minus the number of blue marbles. So that's going to be 10 minus 3, which is 7. Any thoughts or questions on this one?
No, please.
All right, we'll move on to the third one. So for this question, I actually had a typo in the question that made it a little bit harder. We can solve this version of the question, and then I'll also share what the intended question was, and then maybe as an exercise, we can think about it. So this one says, I have a biased coin. Probability of flipping heads is not equal to the probability of flipping tails, and the probability of flipping heads is not 0. Can you see my?
Yeah, it's
No,
frozen on the previous question.
Yeah, I thought so. Let me try resharing. Okay, can you see problem 3 now?
Yes.
Yeah.
All right, perfect. So there's a biased coin, there's probability of flipping heads that's not equal to the probability of flipping tails, and it's not 0. And so now we know that when the coin is flipped 4 times, the probability of getting exactly 1 head is the same as the probability of getting exactly 4 heads. And then the question says, what's the probability of getting exactly 3 heads when you flip the coin 4 times? So what we could do here is also assign a variable to this. So we could say, okay, let's say let P equal the probability of flipping heads.
I don't know if it's only me, but your screen is still frozen on only this question. I don't see what you're writing.
Okay, give me a sec. Let me try reconnecting here. Sorry, 1 second. All right, let me try this. Cool. So all I did here, all I wrote down was just let's let variable P denote the probability that when we flip the coin once, we have the probability of flipping heads. So then we also know that the probability of not flipping heads once is going to be 1 minus P, because we either flip heads or we don't flip heads. So now we can write an equation to capture this statement. When the coin is flipped 4 times, the probability of getting exactly 1 head is the same as the probability of getting exactly 4 heads. So when we flip a coin 4 times, what's the probability of getting exactly 4 heads if the probability of getting one head when you flip once is P. Any thoughts?
Isn't it still, they're exactly the same?
So for example, like say we have a regular coin and the probability of getting heads is 1/2 and the probability of getting tails is 1/2. What's the probability that if I flip the coin 4 times, I get 4 heads?
That would be half to the power 4.
Power 4.
Yeah. So in this case, instead of it being 1/2, when we flip the coin once, the probability of getting heads is just P. So then what's the probability of getting 4 heads if I flip the coin 4 times?
Then would that be 1 minus P times 1 minus P times 1 minus P times P?
That's the first part. So the probability of getting 4 heads out of 4 is going to be P to the 4. And then the probability of getting 1 head out of 4 is, what did you say it was?
1 minus P to the 3rd times P.
Okay, that's close. So there's actually going to be, you want to do 4 times that because there's kind of 4 different ways you could get this. So you could do heads, tails, 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 or tails, heads, tails, 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 heads, tails, or tails, 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 heads. So there's 4 choose one ways to pick which of the 4 rolls is going to be a head. And then for each of these cases, the probability that each case happens is going to be 1 minus P cubed times P. So going back to this statement, it says when the coins flip 4 times, these 2 probabilities are equal. So if we write that, we get P to the 4th equals 4 times 1 minus P cubed times P. Before I move forward with this, let's write out what's the probability of getting exactly 3 heads when the coin is flipped 4 times.
Would that be 4 times P to the 3rd times 1 minus P?
Yeah, so that's going to be 4 times 1 minus P times P cubed. Cool. So now let's put these together. So these 2 are equal. So this gives us, I'll just write it over here. This gives us 4 times 1 minus P cubed times P equals P to the 4th. And since we know the probability of flipping heads is not 0, then we can cancel P from both sides. So we can basically divide both sides of the equation by P. So we get 4 times 1 minus P cubed equals P cubed. So what we could do here is we want to solve for P. So we can say maybe divide both sides by 1 minus P. So we could get 4 equals P cubed over 1 minus P cubed. And since we know P is sort of a real number, we could take the cube root on both sides. So we could get cube root of 4 equals P over 1 minus P. And then if we multiply both sides by 1 minus P, we get cube root of 4 minus cube root of 4 times P equals P. To move this to the side, so we get cube root of 4 equals 1 plus cube root of 4 P. So P equals cube root of 4 over 1 plus cube root of 4. And then that's the probability of getting heads. The probability of getting tails is going to be 1 over 1 plus cube root of 4. Any questions so far? All right, so now we've solved for P. And now remember what we're looking for is actually this quantity over here. What's the probability of getting 3 heads out of 4? So in order to calculate this, we can use what we just found out. So we want to compute 4 times 1 minus P times P cubed. One kind of nice thing you could look at is this equation here. P cubed equals 4 times 1 minus P cubed. So if I plug this in to here, then I get this equals 4 times 1 minus P times 4 times 1 minus P cubed, which equals 16 times 1 minus P to the 4th. So this, if we now plug in this over here, then we get, this is 16 over 1 plus cube root of 4 to the 4th power. And I'm not going to expand that out because it doesn't really simplify to something really nice, but that's going to be the probability that we get. Does anyone have any questions about this, how we solved it?
I was just wondering on how you were able to simplify the equations, how you were able to simplify the equations enough to get the value of P3 out of 4. I'm not really sure on that one.
Oh yeah, so basically we have this quantity 4 times 1 minus P times P cubed. And then all I did was I replaced P cubed with this quantity over here, which we know from our relationship over here.
Okay.
And then to get from this step to this step, I just multiplied the 4's together and then the 1 minus P's together. Any other questions or thoughts? So what I meant to write in this question was actually that the probability of getting exactly 1 head is the probability of getting exactly 2 heads. So I guess it's hard to see. Exactly 2 heads. So maybe as an exercise, you all can try that problem. Post your answer on Piazza if you want to check it with me. And that one should give you sort of a nicer fraction answer. All right. So now we move on to a couple of questions on conditional probability, which was the second part of our lecture earlier this week. So this question says there's 2 bags of marbles. Bag A contains 5 red marbles and 2 yellow marbles. Bag B contains 3 red marbles and 5 yellow marbles. A bag is chosen at random, and then a marble is taken at random from the bag. If the chosen marble is red, what's the probability that the chosen bag was bag A? So any thoughts on this problem? So if we remember our conditional probability, when we say if the chosen marble is red, what's the probability that the chosen bag was bag A? We could write
The
that.
screen has been zoomed in, so we only see a portion of the screen. Okay, yeah, that's better. Thank you.
Yeah, sorry about that. So if I write this as kind of the conditional probability format, then we want to say what's the probability that the chosen bag was bag A? The probability we choose bag A, given that the end chosen marble is red. Sorry. So this is the quantity that we want to find. And the way that we calculate this is this equals the probability that we chose bag A and the chosen marble is red over the probability that the chosen marble is red. So now we can compute each of these probabilities and take the ratio and get the conditional probability. So what's the probability that we chose bag A and then we chose a red marble? Any thoughts on that?
So since the bags are chosen at random, they both have an equally likely chance of being chosen. So for to choose bag A, it's half. And then if we sum the total amount of marbles, which is 15, and find out the total amount of red marbles, which is 8, it's times 8 over 15.
So that's close. Since we're calculating the probability that we chose bag A and chose a red marble, that means we have a 1/2 probability of choosing bag A. And then because we're then only taking marbles from bag A, we want to multiply this probability by, what's in bag A. So in bag A, there's 5 red marbles and 2 yellow marbles. So it's going to be 5/7. Does everyone see why that is? Any questions? All right, so now we'll get to using the information about bag B as well. So what's the probability that the chosen marble is red?
Half times 3/8.
Half times 3/8. So that's the probability that we chose bag B and we chose red marble. So we can actually solve this one using casework. So the probability that the chosen marble is red can happen in 2 ways. So we can either choose bag A and then pick a red marble, or we could choose bag B and then pick a red marble. So we could say this equals the probability we choose bag A and chose then a red marble plus the probability that we chose bag B and then chose a red marble. So the first part we just calculated above, that's 1/2 times 5/7. And then what you said, was that the probability that we chose bag B is going to be 1/2. And then the probability that we choose a red marble from there is 3/8. Any questions so far? All right, so now we can plug this in to this expression. So this probability equals, on the numerator, it's 1/2 times 5/7. And in the denominator, it's 1/2 times 5/7 plus 1/2 times 3/8. And to make this a little bit easier to compute, we can actually cancel out the 1/2 over here. It's kind of like multiplying top and bottom by 2. And then this will give us 5/7 over, we can have a common denominator of 56. So that's going to be 5 times 8, sorry. 5 times 8 over 56 plus 3 times 7 over 56, which is going to be 5/7 over 61 over 56. So this is going to be 5 over 7 times 56 over 61. This 7 goes in 56 8 times, so this is going to be 40 over 61. Any questions on this one?
I was just wondering why, when we were finding the denominator, we couldn't sum the total number of marbles.
So the reason we didn't do that is because the probability that we pick the probability that each marble is going to be picked is not the same. So for example, if you were to label all the marbles, the chance that you pick a marble in bag A is going to be a specific marble in bag A is going to be 1/2 times 1 over the number of marbles in bag A. But that's the number of marbles in bag A is different than the number of marbles in bag B. So the chance that you pick any specific marble in bag B is going to be 1/2 times 1 over the number of marbles in bag B. We can't sum them because that would kind of assume that you have an equal chance of picking any marble, but that's not true between the two bags.
Okay, thank you.
Yeah, a more obvious example of this would be, say you have 2 bags of marbles and one bag has 1 marble and one bag has 1,000 marbles, but you first pick one bag randomly. Then in that case, you could see that the chance of picking that 1 marble in the bag with 1 marble is just gonna be 1/2 because you have a half chance of picking that bag. And then once you pick that bag, you have to pick that marble. Whereas if you have a bag of 1,000 marbles, then you have a half chance of picking that bag. But then once you pick that bag, you have a 1/1000th chance of picking any marble there. And so we can't just sum them. It's not gonna be the same. All right, I'll move on to problem 5. So this one, I think quite a few people got this problem. This one says Marie randomly chooses an integer m between 1 and 10,000 inclusive. If m is a multiple of 9, what is the probability that m is a perfect square? So the kind of conditional probability we want to calculate here is probability m is a perfect square given m is a multiple of 9. Does anyone want to share how they did this problem?
I didn't go exactly by this method. I knew that 9 itself is a square number, which is 3 squared. So I'm coming. So and sorry, 10,000 is also a square number, which is 100 squared.
Mm-hmm.
So if you just find the square root of both of them.
Okay, so let's first see what are the quantities we need to count. So for this, this is actually going to be, so there's actually a couple ways we can, maybe I'll share what it is, and then I can also share how that relates to the formula we used above. So I I think probably what a lot of you did is we want to count the number of numbers between 1 and 10,000 such that numbers of 1 to 10,000 that are perfect squares and multiples of 9. And then the denominator is going to be number of multiples of 9 between 1 to 1,000, or sorry, 1 to 10,000. Is this what most folks did? And as a
tried to go that way.
oh, sorry, go ahead.
I tried to go that way, but then I realized it wasn't really working out. So I tried to find some pattern in multiples of 9, and I was looking around that area, but I didn't really get it.
Okay. Okay, cool. So it sounds like but you started off by kind of, in order to calculate this probability, we need to find these two numbers. Kind of relating this to our formula earlier, we could also say this is a probability M is a perfect square and multiple of 9 over the probability M is a multiple of 9, which is going to give us basically this thing, because first we want to count the number of possibilities of perfect squares that are multiples of 9 over the total number of integers, right? And then the bottom probability is going to be number of multiples of 9 over 10,000. And then we could cancel out these 10,000s. So that would give us this. So let's go to the counting problem. The denominator is a little bit easier. So how many multiples of 9 are in 1 to 10,000? How do we count that? So it's sort of like how many multiples of 9 are in kind of the sequence, 9, 18, 27, all the way up to kind of 10,000. Any thoughts on that sub-problem?
Well, if we just subtract 1 from 10,000, we get the nearest multiple of 9, which is 9,999. So when you just divide that by 9, you get 1,111.
Okay, so what you're saying is that the largest multiple of 9 less than or equal to 10,000 is 9,999. And so we want to count how many numbers are there in this kind of sequence, 9, 18, 27, all the way up to 9,999. And if we divide all of these by 9, then we get this is equal to counting 1, 2, 3, all the way up to 1, 1, 1, 1. So this is going to be 1, 1, 1, 1. Cool. So the second quantity we want to find is number of perfect squares that are multiples of 9. Between 1 to 1,000 or 10,000. So how do we count this? Does anyone want to share how they did it?
Well, 10,000 is already a square number. It's 100 squared.
Mm-hmm.
So that would mean that the first 100 square numbers can be found within 10,000.
Okay. So we know that there's 100 squares between 1 to 10,000. we need to count how many of those squares are multiples of 9. So how would we do that?
Divide
Maybe
the
what
100 by 9.
Sorry, does someone else want to say something too?
what I was saying was, since 9 is 3 squared, we could just find all the multiples from 1 to 100. All those multiples, when you square them, they would have 2 powers of 3 multiple of 9.
Yeah, that's right. So we notice that 9 is 3 squared. So we want to basically see out of the numbers 1 squared, 2 squared, 3 squared, all the way to 100 squared, how many of them have a factor of 3 squared in it. And the way that we do that is we could basically we would look at anything that, any multiple of 3, if we square it, that's going to be a multiple of 9. So all the perfect squares that are multiples of 9 are going to be 3 squared, 6 squared, 9 squared, 12 squared, etc. And then the largest multiple of 3 less than 100 is going to be 99 squared. So this is going to be the number of elements in the sequence 3 squared, 6 squared, 9 squared, 12 squared, to 99 squared. And if we kind of want to find a correspondence here, we could say this kind of corresponds to 1, 2, 3, 4, 33. By kind of taking the square root and then dividing by 3. So then this will give us 33 numbers in the sequence. So then going back to our probability, let's call this P, then P equals 33 over 1111. And then we could just simplify this because both the numerator and the denominator are divisible by 11. So this will give us 3 over 101. Any questions or thoughts about this one?
Oh, please.
All right, I'll go to the last question. This one was a little bit similar, but not exactly the same as the last question of the test last week. So this one says, Lily randomly chooses value X and Y. And I kind of clarified, since last time a lot of people assume they're integers, that these are not necessarily integers. So for example, X could be 0.5, right? Such that X is between 0 and 6, and Y is between -4 and 4. But now the problem says, so previously last week, the problem said, what is the probability that X plus Y is greater than or equal to 0 and X plus Y is less than or equal to, I think last week I said 3. But this one's a little bit different. It says if X plus Y is greater than or equal to 0, what's the probability that X plus Y is less than or equal to 4? So let's start by graphing this out, and then we can talk about how to actually compute the probability. So let's draw this axis. So let's first graph out X is between 0 and 6. 1, 2, 3, 4, 5, 6. So this is X less than or equal to 6. It's going to be this way. This is the y-axis. This is X greater than or equal to 0 is going to be this way. And then for -4 is less than or equal to y is less than or equal to 4. And we would graph it. like so. This isn't very evenly spaced, sorry. Try one time. So this is going to be the line y is less than or equal to 4, sort of shading this way. And this is the line y is greater than or equal to -4, kind of shading this way. Any questions so far? I just graphed this and this. And so the region that we care about here is so far just this region over here. That represents this region I just highlighted. All right, so now let's graph these two other lines. I'll use a different color, maybe blue. So x plus y is greater than or equal to 0. So that's going to look like, basically it goes through the origin, has slope -1, because it's y is greater than or equal to -x. So that's going to go through, you know, here. It's going to go through 4, -4, and 0, 0. So looks something like this. And that's going to be kind of over here in this direction. And then the last line that I'll draw, I'll use like an orange color, is x plus y is less than or equal to 4. So this, you know, you could rewrite as in slope intercept form is -x plus 4. So it also has slope of -1 and it crosses the y-axis at 4. So this is going to be 0, 4, and it's going to cross over here at 4, 0, and also at 6, -2. So it's going to look something like this. And less than or equal to 4 is kind of in this direction. Any questions so far? So here I just graphed these two inequalities onto the same graph. All right. So now let's get back to computing the probability. So we want to say, what's the probability that x plus y is less than or equal to 4? And the difference from last time it was x plus y is less than or equal to 4 and x plus y is greater than or equal to 0. But here I'm asking for the probability that x plus y is less than or equal to 4, given that x plus y is greater than or equal to 0. So this is going to be the probability that x plus y is less than or equal to 4 and x plus y, which is what we calculated last week, or similar to what we calculated last week. But we also need to divide that by the probability that x plus y is greater than or equal to 0. And we can simplify this by saying this is the area of the graph where x plus y is less than or equal to 4 and x plus y is greater than or equal to 0. So maybe I'll use, so let's do the bottom. So the bottom, we could simplify this to be the area of the part of the graph that is just x plus y is greater than or equal to 0. So that's going to be It's a little light. That's going to be this area over here. So area of the yellow region. And then the top is going to be, I'll use a different color like orange. The area of this region where it's greater than or equal to 0 and less than or equal to 4. Any questions so far?
No, please.
All right. So now let's compute the area of, let's do the yellow region first. So remember the yellow region is actually the yellow region is actually this whole region over here. Maybe I'll use, it's actually this whole region. So how do we compute this region?
First, we have to
Yes.
figure out the area of the square or rectangle.
Okay, so what's the area of the rectangle?
That's going to be 6 times 8, I guess. Yep,
Yeah, so this is 6, this is 8.
times 8. Yep.
Cool. So
And
this
then
is the area of rectangle.
we
What's
have
that?
to figure out the area of the two of the triangles.
Okay, so for the bottom, we just need to figure out this triangle down here. So what's the area of this triangle?
That's 8.
Yeah, so we have the side length of 4 and this side length of 4. So the area of this triangle is 4 times 4 over 2, which is 8. Cool. So this simplifies to 48 minus 8, which is 40. And then the area of the orange part, which is just in between, how do we calculate the area of that?
Well, that would be the area of the two triangles, the one in the bottom corner and the one in the top. So it would be 48, sorry, minus 4 times 4 over 2, minus 6 times 6 over 2. 6 times 6.
Yeah, so this is 6 and this is 6. So we want to subtract out both triangles.
Come in.
So, yeah.
Wondering if you have classes.
So this is going to be 48 minus 8 minus 6 times 6 over 2 is 18. So this is going to give us 22 over 40. So the answer is going to be 11 over 20.
Shouldn't it be 11 or 24?
So it would be 11 over 24 if I said, what is the probability that, so probability that x plus y is less than or equal to 4 and x plus y is greater than or equal to 0. In that case, you would take the area of the middle part, which is, so this one was 22, right? You would take 22 over the area of the total rectangle, which is 48. So that would give us 11 over 24. But this is saying if x is plus y is greater than or equal to 0, what's the probability that x plus y is less than or equal to 4? So it's asking a different probability, which is this conditional probability. And so we need to take this quantity at the bottom and also divide it by the probability that x plus y is greater than or equal to 0. So if we want to calculate that directly, probability x plus y is greater than or equal to 0, that's going to be 40 over 48, which is, for simplicity, just 20 over 24. And so then if we take 11 over 24 divided by 20 over 24, we're going to get 11 over 20. So this is the difference between like conditional probability and just like the probability that two things happen. So the probability that x plus y is less than or equal to 4 conditioned on the fact that x plus y is greater than 0 is different from the probability that both of them happen. Any other questions on this one? All right, I want to make sure you guys have enough time to go over the other part of the test. So sorry it took a little bit longer, but next Matthew will go over the problems from his side.
Hello.
I'm Mr. Crawford.
Okay. Sorry, I'm getting set up here. Oop. Okay, let's take a look at problem number 1. This is a Huron's formula problem. And let's walk through what the computations look like. Let's see, first we want our perimeter and our semi-perimeter. So we add those up and we get 26. So S equals 13. And now we compute semi-perimeter times each side minus the semi-perimeter. So 13 minus 7, 13 minus 9, and 13 minus 10. And Huron's formula is kind of the can opener of basic geometry. It really does the job when we don't really have some nice symmetry or other circumstance to be working with. By the way, there were people who did not simplify their answer here. And I went ahead and counted those wrong. Just note that anytime you're dealing with radicals, it's probably best, especially on a test. You know, part of the reason we have simplified form is so that we have like a simplest way to communicate numbers. So, you know, always reduce things to simplified form, or at least lean toward doing so. And in this case, you know, you can chop up those factors. 6 is 2 times 3, 4 is 2 times 2, and then we have a 3. So it doesn't take terribly long to go ahead and work through the simplification. Okay, let's take a look at number 3. We have an angle bisector. Oops, that looks not like an angle bisector. That looks closer. And by the angle bisector theorem, well, I'll go ahead and put down some labels right here. By the angle bisector theorem, AB is to BD, as AC is to CD. Each side is in proportion to the length of its shadow. And then we plug in, we know that AB is 20. And I'm just gonna call, we'll call BD X and CD Y. So we know that 20Y equals 24X. We also know that X plus Y is 22. And the way I might go about doing this, I might just say, okay, I'm gonna solve for X and Y here. If one of these is 10, the other one is 22 minus 10, which is 12. So X times Y equals 120. Any questions or thoughts about this one? Okay, let's move to number 5. So 5 was one of the difficult problems on the test. Nobody got this one correct, so let's talk about this one from beginning to end. This is a challenging problem if you haven't seen something like it before. So we've got a square. And we've got these segments of length 2. Let's draw a few of these and kind of get a grip of where the locus of points that we're talking about is. We could draw these kind of around a corner with 2 different endpoints on one side. We could draw these going along one side. And, well, these at the corner kind of cascade around and give us this wave pattern. But what we're interested in is the midpoint, anywhere we are, the midpoint of this segment right here. If you make a really nice drawing, you might be able to figure out where things are. I did not measure things out very well in order to follow along and try to do this. Instead, what I'm going to do is I'm going to examine, okay, let's say that we have one of these such segments. Let's focus on it. Here is the midpoint. What did we learn about the midpoint of a right triangle during the second half of Wednesday's class?
It is the circumcenter of a circle.
It is the circumcenter of the triangle. Very good, Salorm. So right now, you're the closest to solving this problem. What is true about that midpoint while this segment is around that corner?
That it touches the corner.
What do you mean it touches the corner?
The circumference of the circle touches the corner of the square.
That's right. So what is the distance from that circumcenter to the corner?
Half the distance of the line segment.
Right. So it's distance 1. So what we get in the corner, the locus of the midpoints as the green segment moves around that corner is a quarter circle of radius 1. So now if we follow the segment up the side, the midpoint just traces out a straight path like that. But then again, around this corner, it forms a quarter circle. Then it traces out a segment of length 1, and then another quarter circle, and then finally, we get back to where we started. This is the figure whose area we are trying to find. It's the square with 4 quarter circles cut out of it. So what is its area?
The area will be,
Since
Go ahead, Norley.
would it be the area of the square minus the cutout areas?
Yes, it's the area of the square minus the cutout areas. So we have a funky area problem.
Well, since we just found the circumcenter, we know that it's equidistant from each. We know that it's equidistant from each of the corners of each of the vertices of the triangle. We know that it's on the midpoint, which means that the distance from one vertex to the midpoint of the hypotenuse is 1. So we can say the radius of our quarter circles is 1.
Yes. So what is the sum of the areas of the cutouts?
Since they are all right angles and they are 4, they would make a full circle.
That's correct.
So it's basically the big square minus 1 circle with the length A with radius 1.
And that is our answer. Any questions or thoughts about this one? Yeah, this is an unusual geometry problem when, before you have worked as much with locus problems, remember this one. This is a problem that, locus problems can be difficult. There's a lot of Olympiad geometry that winds up being like this, where you're trying to find something in a diagram that might be constant, some length that might be constant, or a sum of lengths that might be constant. And this is a good problem to get you started with those types of Olympiad locus problems, or with deeper geometry period, Olympiad or not. Okay, let's take a look at number 7. So some people got this one. There were some right answers to this. I can't remember how many, but it was definitely not as hard as the last problem. So once again, we have a problem where we can apply Huron's formula. We've got a perimeter and we've got integer side lengths. So our semi-perimeter is 11. So what we're really looking for is the largest possible value of this expression where A, B, and C add up to 22. Now, in order to find the largest possible value of this whole expression, we find the largest possible value of what is underneath the square root. And in order to find the largest possible value of what's underneath the square root, we can really focus in on just this part that has variables. And how is it that we want to arrange A, B, and C? Now, my guess is that most of you who got this one right played with the possible values. You plugged in different numbers to see what you would get. And you eventually found that you wanted A, B, and C to be as close as possible together. So I'm gonna call that a conjecture. We want, we want 11 minus A, 11 minus B, and 11 minus C to be closest together. And that's not very well defined yet, but we'll get away with making it intuitive. But we notice that 11 minus A plus 11 minus B plus 11 minus C, well, that's constant. It's 33 minus the perimeter, which is just 11. And let's talk about a lemma here. The product of two positive numbers is largest when their difference is smallest. Now, I say it this way. We could just say, okay, let's let the difference be 0. But I like putting it this way because we may be in a situation where we have constraints, like the current situation. We can't just make them all equal. We have to deal with integers in that problem. But let's just work 2 variables at a time. If we have 2 variables, and let's say that we make them the side lengths of a rectangle, but we have a constant sum. Actually, I'm going to make it 2s so that the perimeter of this figure is 4s. And you'll see why I'm going to use 2s in just a moment. So x plus y is 2s. We could rewrite x and y. We could let x be s minus d and y be s plus d. And I'm going to call d the deviation. Deviation from the arithmetic mean of the 2 of those numbers. So what is the area? Well, the area of this figure is x times y, which is s minus d times s plus d, which is equal to s squared minus d squared. Now here's the thing, s is a constant. It was decided on as to be the thing that we're holding constant. We're not changing in this problem. By the way, we call this an isoparametric problem. I think we solved 1 or 2 isoparametric problems previously, right? Well, in this case, if we want s squared minus d squared to be largest, then we want d squared to be smallest, right? By the trivial inequality, d squared is at least 0. And for positive values of d, and we can hold d to be non-negative. For non-negative values of d, d squared is monotonically increasing, meaning that it only goes up as d goes up. So we have d squared is at least 0. Negative d squared is less than or equal to 0. So s squared minus d squared is less than or equal to s squared. So just in case we want something like an equality case. But the point is, if you have 2 numbers that sum to be the same, the area gets bigger, their product gets bigger as we move those numbers together, because the deviation between them gets smaller, and that determines how much less than optimal we wind up. So in this problem, we're dealing with a product of 3 numbers. But let's say for a moment that we pick a value of x, a value of a. Let's say one of the side lengths is 2, for instance. Well, that means that the sum of the other 2 side lengths I want to do it that way now. I'm going to make a little bit bigger. Let's say that a equals 5. And then b plus c equals 17. then 11 minus b plus 11 minus c is equal to 5. Then, if we wanted to, if these numbers were not as close as possible together, and the closest we can make them since they're integers is 1 apart, then we don't have the greatest possible product that we could have. So if you ever have any two of the three numbers that are further than 1 apart, then you can take one away from them and add it to the other one, and you will wind up with a larger product. Have I made this clear, this part?
I'm still not 100% sure what you mean when you say like the difference must be smallest, because when you say the product of two positive numbers is largest when their difference is smallest, I still don't understand what exactly you mean, because I'm thinking like 1 times 1,000, that's pretty big, but when you do 1 times 3, that's smaller than.
Okay, but 1 times 1,000, it's their sum that we're holding constant. So you don't compare it to 1 times 3. If you compare 1 times 1,000 to 2 times 999, 2 times 999 is bigger. It's 1,998. What's bigger than that? 3 times 998, which is 2,994.
So we have to keep one of them constant.
If we're keeping the sum of them constant, not one of them. Oh, you mean among the 3 variables?
Yeah.
Yes. And instead of 11 minus a, 11 minus b, and 11 minus c, perhaps we should have used something like x times y times z, where x plus y plus c is a constant 11. That'll probably make this easier to talk about. And in this example, if I said, hey, x happens to be 6, so y plus c is 5. Well, we could have 6 times 1 times 4, or we could have 6 times 2 times 3. Well, 6 times 2 times 3 is clearly larger. So we're never going to have 2 of the variables be more than 1 apart. We're going to move them toward the middle, move them toward the middle. And what's bigger than 6 times 2 times 3? Well, 5 times 3 times 3 would be bigger than that. And then 4 times 4 times 3 would be even bigger than that. If you can ever move 2 of the numbers closer together, if 2 of the numbers are ever further apart than 1, you don't have an optimal largest product. But we do wind up with the largest product with exactly these numbers right here, which gives an area of 11 times 4 times 4 times 3, which is 4 root 33. Any questions or thoughts about this one? Okay, let's talk about number 9. So this was another pretty hard problem. There was one correct answer on the exam to this problem, and I can't remember who that was off the top of my head. But by the way, the high score for this exam was Mon Vendra, so nicely done. So let's see, find the number of distinct right triangles with sides of integer length in one leg equal to 60. So I'm going to rewrite this as a squared plus 60 squared equals c squared. By the way, I should have said non-degenerate right triangles, because perhaps we could have 0, 60, and 60. And if somebody had put 14 as the answer, I would have counted it correct, but the answer is going to be 13. But let's walk through this. What we want is the number of ordered pairs of positive integers, AC, that satisfy this equation. Have we talked about that big bold Z
Yeah, we have.
Okay, I thought we did. I thought we did on week 1. I just wanted to be sure. So if we rearrange this equation right here, we can get c squared minus a squared equals 60 squared. And then c plus a times c minus a equals, and I'm going to work out the prime factorization of the right-hand side. We can find the prime factorization of 60 and then square it, which is nice. And this is a problem where I posted an additional lesson, and I can't remember if I included a video to it or not, but I call this method factoring is factoring, where we have a Diophantine equation, and on one side we do the algebraic factorization, on the other side we do the prime factorization, and then we compare. Now, here's the thing. We want c plus a times c minus a to be a pair of factors of 3600. I just want to take a quick peek at what factors like that look like. Well, we could have 1 times 3600, 2 times 1800, 3 times 1200, 4 times 900, but not all of these are going to work, right? We could count these up, and in total, how many divisors are there of 3600?
Um, 45.
Yes, good. 5 times 3 times 3, add 1 to each exponent and multiply them together. So what we have here, well, if we wrote all the way down to 3600 times 1, we'd have 45 pairs, but we don't need them all. In the middle, there's 60 times 60, and we can stop there. And we have 23 pairs, but 23 is not our answer. This would give us pairs of values of c plus a and c minus a, but not all of them allow c and a to both be integers, right? One example is c plus a equals 3600 and c minus a is 1. Of course, c plus a needs to be larger than c minus a because we're dealing with positive numbers. But if we look at this pair right here and we solve this, we get c equals 1800.5 and a equals 1799.5. On the other hand, if c plus a equals 1800 and c minus a equals 2, we do get integers. We get c equals 901 and a equals 899. And so we need to ask ourselves, when is it that we're going to get integers? Who has an answer for that? When will we get integers to one of these systems of equations, and when will we not?
Is it when the factors are even?
In this case, it is. In particular, they need to have the same parity. And I don't know if I've used that word with you before. Is this a familiar word to you all?
No, please.
Parity is the property of being even or odd. It's kind of like we say the sign of a number is whether it's positive or negative. The parity of a number is whether it's even or odd. So in this case, we could add these equations and get 2c equals 1802. And that means that c is half the sum of those two numbers. So they either need to be both even or both odd in order for that to be an integer. Similarly, we can subtract them. And that difference is 2a. So that needs to be even. meaning we need to have the same parity so that we can divide by 2 upon subtraction. So we need to kind of go back and ask ourselves a second time over, in how many ways can we split this thing up into divisors? Oops, let me try that again. In how many ways can we split this thing up into divisors so that they have the same parity? And in this case, that means that they're both going to be even. So we want to know the number of ways to break 3,600 into 2 even divisors. So let's see, 3,600 equals 2m times 2n for positive integers m and n. Now we can divide this whole equation by 4 and say, hey, look, we're actually counting the divisor pairs of m times n. Okay, m times, okay, so we have divisor pairs like 900 times 1, 899, 450 times 2, and so on up to 1 times 900. But we don't have to go this far because we remember that one of these divisor pairs needs to be 2 times c minus a, and the other one is, oh no, wait a minute, just c minus a, pardon. One of them is c plus a and the other one is c minus a. So we only go to the middle where we have 30 times 30, which is actually, when we multiply the 2's back in, 60 times 60. But we're not going to care about that one, right? In total, we have 3 times 3 times 3, 27 divisors. And when we pair them up, we stop at the middle. So we take a look at the first 14, but this one is not going to give us a solution. If c plus a is 60, and c minus a is also 60, then c is 60 and a is 0. And so we have a 0 leg of that right triangle. And so we'll go ahead and toss that one out, and we'll say that the other previous, if there are 27 pairs in this list, and this is the middle, this is 14, we have 13 others, each one of which will give us a Pythagorean triple. And just to feel comfortable with this, let's take a look at a couple of the examples. Let's say that we choose 900 times 1, which corresponds to 1,800 times 2. Then c plus a is 1802, and c, wait a minute, sorry. I'll just jump to c equals 901, and a equals 899. So that c plus a equals 1,800 and c minus a equals 2. And that corresponds to this one right here, that pair of divisors of 900. And it is true that an 899, 60, 901 Pythagorean triple exists. If you work that out, well, let's go ahead and do it. 899 squared is 80201, and then plus 3,600 equals 811,801. And that is 901 squared. I'm going to do one more, just to pick one kind of from the middle. Let's do 900 as 90 times 10, in which case we would have c plus a. 90 times 10 in here would correspond to 180 times 20. So if we have c plus a is 180 and c minus a is 20, then C equals 100, and A equals 80. And we have a very familiar 3, 4, 5 proportional right triangle. So in total, we have 13 possible non-degenerate right triangles with sides of integer length. So whoever got this one, great job. Great job putting together our combination number theory right triangle lesson that we talked about, and going back to our first couple of weeks of number theory.
And Mr. Crawford, is there something like a theorem for finding the Pythagorean triples for a side which has an even number? Because I think I found something.
There is a generator, and we actually did a lot of the work behind getting there. We didn't have time to do it all, and I consider that, you know, it's a little bit more of an advanced lesson. I would have wanted to do more number theory with you all if we were going to go quite that far, but we actually did a lot of the work behind the method for generating all possible Pythagorean triples. And for those of you who are interested in this, if you go on the internet, you know, you'll probably find somewhere, maybe even me, I may have some curriculum on the internet somewhere that walks through this, or maybe we'll do a lesson on that some other time in the future. Okay, let's take a look at the last of the geometry problems, number 11. And there were some people with good complete proofs to this, which was good to see. So if we have a triangle, there we go. If we have a triangle and we have an incircle, and we're trying to find the area of this triangle. Well, the thing that's special about the incircle, or one of the things that's special about it, is that it has a constant radius, as circles do, and that radius hits all 3 of the different sides. That right there, that is a constant. And when we can grasp onto an invariant, I'm going to use that word, let's introduce that word. An invariant is something that doesn't change. And we make use of invariants in all kinds of mathematics, but maybe especially so in geometry. Among the elementary mathematics, perhaps it's most important that we use it in geometry. So what we can use it for in this case is the height of a triangle. We can divide the big triangle up into 3 smaller triangles. And for each one of those, I'll highlight this one right here, and we'll call the incenter I. So this is triangle IBC, and the area of triangle IBC is the base times the height divided by 2. And the base is A in this case, so A times R divided by 2. In total, this means the area of ABC is the area of IAB plus area of IBC plus the area of ICA. And these areas are C times R over 2 plus A times R over 2 plus B times R over 2. And if we factor out the R, we get R times A plus B plus C over 2. And that's just R times the semiperimeter. So that is one more formula for the area of a triangle that you can tuck in your pocket and make useful at times. Any questions or thoughts about this one? Any questions or thoughts? Oh, go ahead, Salorm.
So could we, if we were to, how would we use this to the semi-perimeter in this sort of an equation? Because I'm not sure how how the semi-perimeter is helping here. I mean, I can track how you got to that final answer, but if we had the semi-perimeter, like, let's say outside of the algebra, like, how does it actually work? Because I don't really understand that part.
Maybe I'm not understanding your question. What do you mean, the semi-perimeter outside of the algebra? Can you talk through like a scenario? Like, what are you asking?
Like, I'm asking how knowing half the perimeter of the actual object and multiplying it against the radius helps with finding the radius of the circle. Like, is the semi-perimeter somehow found within the circle or something like that?
No, so, you know, R and S do not have any particularly special relationship. You could find the maximum of R in terms of S. You know, there is an inequality that relates that to that, but it's, you know, for the purpose of this formula, just think of them as two of the variables in a problem, the same way that you might think of the base and the height as two different dimensional variables in a problem like this.
Okay, thank you.
Mr. Kura, please, I found like how to find the other legs of a right angle triangle when you are given one answer using the Pythagorean triples. Like if you have a side which is 60, then you can write it in the prime factorization form as 2 times 30 squared times 2. So the other side will be 30 squared plus 1 and 30 squared minus 1.
Oh, that's true. There is a, that is one of the kind of families of Pythagorean triples. And an example of that is 8, 15, 17. And let's see, 10, 24, 26. This one is not primitive, but once we go up to 12, 35, 37, we have another one. Basically, for the even squares, so let's say 4n squared minus 1 and 4n squared plus 1. Let's say those are B and C in a given right triangle for some integer n. So a squared equals c squared minus b squared, which is c plus b times c minus b. And c plus b in this case is 8n squared. And oops, c minus b is 2. So we have 16n squared is a squared. So a would just be 4n. So that right there is a primitive Pythagorean triple. And if n equals 15, you get one of our triangles from the earlier problem, which is 60, 899, 901. Any other questions or thoughts about anything on the test? Okay, I just want to mention to say that it's been a pleasure to work with all of you. As some of you know, I'm going to be talking with Joel about the possibility of having some further lessons. But if I don't see you again, I greatly enjoyed the last 6 weeks of this summer and talking math problems with you all and walking through this experience. But I think that I'm going to see you again in the future.
Yeah, and also it was really fun to teach you all, and hopefully we'll cross paths in the future too.
Okay. Thank you. It's been a pleasure of mine as well.
Yeah, these lessons have been really fun. Even when you get an answer wrong, it was just fun to find out how could I have done this differently or how could I have done this better, and just ways to
Yes.
improve general mathematics.
Yeah, it totally is. And I'll go ahead and share this all with you. Nobody, works in Olympiad math and gets all the problems right. If you were getting all the problems right, you're not working at the right level. So, the students who are, making their national teams or winning a medal at the IMO or anything like that, those students took classes like this once upon a time where they didn't get nearly all of the answers right. These things that we walk through are things that mathematicians spent centuries developing the first time around. So to be able to think of everything on your own the first time around is pretty close to impossible, probably just flatly impossible. So the best thing to do is to struggle with hard problems, soak up as much of it as you can, think longer, work more problems, and have fun with it, really. So long as you're having fun, that's the most important thing, because you're going to keep finding stuff. There's no end to it. You're going to keep finding interesting things out there. And some of it may be math, some of it may be engineering, so whatever your interests are. But I'm glad that you all enjoyed it. Take care.
Bye.
Okay, you too. Bye.
Bye.
Bye, everyone.